Hello and welcome to this clip going through an early 2002 chemistry Olympiad question, and this one's about periodic trends. So some of them might be slightly beyond the syllabus, they'll probably be designed to stretch you a little bit, but some of them will be quite accessible as well. So I'll take each one in turn and we can discuss it a little bit in the space at the bottom of the screen. So looking at the first one, it wants sodium, aluminium, silicon and sulfur in order of increasing melting point. So you should be able to work out from the graph out of an A-level textbook, a textbook that's no longer in publication, that it's quite straightforward recall. This is typical of most chemistry Olympiad questions, just to get you moving and settle you down as a candidate so that you don't feel sort of nervous or worried or stressed about the fact you're sitting taking a chemistry Olympiad paper. Now, taking the sodium and the aluminium, you need to think about the charge difference between the cations and the delocalized electrons. So it's clear from the diagram that between sodium and aluminium will be at a higher melting point than sodium. Now, silicon will have a higher lattice strength compared to most metal lattices, but in aluminium, the marked charge difference in its lattice will make it particularly strong and resistant to melting. So therefore, you'll find that aluminium will be slightly higher in its melting point to silicon. And that means that sulfur must have the final lowest melting point. So therefore, the order, so the lowest is sodium, and then S8 has the next highest. Now, we didn't really go into S8 very much, but it's an 8-membered simple molecular lattice. So 8-membered means it's got 8 atoms, which means it's got covalent bonds between those atoms that can't be broken. So 7 covalent sulfur-sulfur bonds can't be broken easily in the S8 ring. Plus you have a large number of London forces that can possibly arise if you look at the diagram. So therefore, that means that sulfur sits between sodium and aluminium in this case. In part B, we've got London forces in hydrogen are very weak because there's only 2 electrons in a molecule. Still London forces in methane, but there's 10 electrons per molecule, so they might be stronger this time. You've got hydrogen bonding happening as well in ammonia, so that strengthens it further. And then ionic bonding in the lithium hydride lattice. So therefore, the energy required to overcome bonds or electron or intermolecular forces increases in that order. So therefore, for the second one, it's H2, CH4, NH3, and finally LiH. So it's interesting also to take a moment to think about why lithium hydride has the strongest. So you've got ionic bonding going on, and you've also got 2 very small ions, so the charge density is quite a significant factor as well. In the third one, you can split them into group 2 elements and group 1 elements. So using the diagram to explain what happens as you go down a group, you can sort the individual elements on each group into which will be smaller, which will be larger. But you've also got to consider that you've got the trend across the period. So you've got period 2 and period 3 as well. And obviously across a period what happens is you have a decrease in the atomic radius because same shielding but a larger number of protons. So organising those into the right order gives us the answer for C there. So if we then move down a bit, it's a similar kind of story, isn't it? So this time we're considering ionic charge, the decreasing radius in cations. So the ionic charge, as it gets bigger, decreases the radius in positively charged ions. So you've also got to think about the number of shells, which obviously increases the radius in positive and negative ions. But if you have negative ions, what's going on is there's going to tend to be a repulsion between the shells, which will push them apart, because the shells themselves are made of negative electrons. So this then allows us to decide what's going on in D, which would be Mg2 plus, then sodium plus, then F minus, then finally Cl minus. Okay. So the next one here wants us to consider increasing electronegativity. And using the electronegativity trends you can remember from your basic A-level chemistry in your first year, this one's quite straightforward. So if we now go down to part F, this one's quite straightforward between silicon and chlorine, because you can clearly highlight that they are more or less in the correct order already. But between phosphorus and sulfur, you need to have a little think about why they're so apparently similar, but they want you to try and discern between them. So looking a bit more closely at the arrangement of electrons in the p subshell, you can see there's repulsion in the p subshell in sulfur, which means that that would reduce its ionization energy, making it easier to remove an electron from the orbital where the repulsion is taking place. So that gives us silicon, followed by sulfur, followed by phosphorus, followed by chlorine. So for the next one, you have to think about multiple bonds in group 6 diatomic molecules. Nitrogen has a triple bond because it's only got 5 electrons in its outer shell, so it needs to share another 3. Oxygen's got 6 electrons in its outer shell, so it needs to share another 2, so it does 2 bonds between its individual atoms. And in addition, you've got to think about, for the halogens, the increase in bond strength is going to be down to how much shielding they have. So bromine has more shielding than chlorine. So that allows us to put oxygen before nitrogen, and that allows us to put bromine before chlorine. Okay, so the next one along is looking at increasing bond angle. So here you have to apply the valence shell electron pair repulsion theory. So if we use the idea that electron pairs repel to get as far apart as possible, we can see that there are analogous examples there between OF2 and water, SiF4 and methane, BF3 we've probably seen in our A-level textbooks. Xenon tetrafluoride you won't have seen before, so let's go and have a look at the actual bond pairs and lone pairs for each one. So for OF2 you have 2 bond pairs, 2 lone pairs. Silicon tetrafluoride you have 4 bond pairs, no lone pairs. For boron trifluoride you have 3 bond pairs, no lone pairs. And for xenon tetrafluoride you'll have a bit of octet expansion, giving 4 bond pairs and 2 lone pairs, so the lone pairs sit on top and bottom of the xenon central atom, meaning the bond pairs go out at 90 degrees to each other. Now on the next one, where you're looking at increasing rate of hydrolysis by aqueous hydroxide ions, that should relate to your haloalkane hydrolysis that you might have done a little bit later on in your first year. So in this case, what drives that is the bond enthalpy between the carbon and the halogen. So therefore, that allows us to think about it in quite a straightforward way. So you may have even done a practical on this where you'd have results and data that would support that kind of order. So in this next one, we need to take into account some of our knowledge from our first year. Metal oxides tend to be bases, non-metal oxides tend to be acids, and sodium chloride is a neutral salt. And the fact behind this metal oxides being bases is that metal oxides react with water to make a metal hydroxide. So that allows us to deal with Na2O and NaCl, because NaCl is a neutral salt. So looking at the two sulfur oxides, drawing out an equation for each one, that gives us two acids, one of which we know is quite a strong acid, H2SO4. So that allows us to think about SO3 being the first in terms of the lowest pH out of all the oxides, then SO2, then NaCl as its neutral, and then Na2O, because we know that will form a base in the presence of water. So this now takes us to the end of the clip. Hopefully it's been a useful roundup of not just periodic trends, but a look at lots of different chemical properties and how they might apply across the periodic table. So until next time, thanks for listening and see you soon.